So we're going to start off with this advanced 3-axis part. And I've got Pro running. Actually, I got premium configuration running. So I got all my 3, 4, and 5-axis toolpaths. As I mentioned before, this is a automotive bezel trim core mold. And this it will be nearly impossible to program using standard configuration. There's just not enough tools and not enough control over the tool to machine this mold core the way it should be machined. So let's go ahead and we'll go ahead and get started. Let's go ahead and do we got our stock. I was mentioning before, it was a stock from selection. So I'm going to select my box stock, and I'm going to go stock from selection, and then I'm going to hide the stock. Okay, so we got the stock here defined. So we don't need to use the align because we did stock from selection, so that stock box was already aligned the way we wanted it. We're going to skip the material for now, and we will go ahead and do a work 0. We'll set it to the stock box, and we will do highest Z in this corner over here, and we'll generate that. Okay, so let's go ahead, and I want to move this up to my setup 3 axis. I have some other operations down here that take a long time to program, so I'm going to show you what they are when I get to them. Okay, so let's go ahead and do 3-axis horizontal roughing. And in horizontal roughing, you don't have to select anything. It'll automatically calculate the stock to remove based on the stock model and the part model. So we'll leave it at that. And we're going to use our large 3/4 inch end mill. Feeds and speeds, we won't mess with these. And clearance plane is set to automatic. And for the cut parameters, for roughing, we're just going to use the default parameters. 10 thousandths tolerance, stocks 25 thousandths. We'll accept all of these default parameters. They all look good for roughing. For the levels, we'll go ahead and use the default parameters of 50%. Now, obviously, when I go through this, I'm using parameters that won't tax the system so that we can get through the webinar. When you actually get this file and ask us, and we'll give you the file, when you get it and run it, use your own parameters as if you would cut it yourself. So we're going to accept that. We'll accept everything else. Change that to 02. Let's generate that. Again, Joe, if there's any questions in the background, feel free to stop me.
Will do.
Okay. So it looks like we got a horizontal roughing operation completed. Let's go ahead and simulate that. Turn the toolpath off so you can see that. So we roughed it out. Now what we're going to do is a professional, in the professional configuration, you have a re-roughing operation. In re-roughing, you do have to simulate the previous operations first. All of the previous operations you have to simulate before you can use the re-roughing, because that's based on the in-process stock model. So we're going to go to 3-axis. We're going to go to re-roughing, and we will select nothing. Let it calculate all the material that it can remove. And for tool, we'll go ahead and use our 1/2 inch end mill. Everything else will be pretty much the same. All the parameters, cut levels, we'll leave that the same. Engage, retract, advanced, we'll change that to 02. Okay.
Yeah, one of the key points here about re-roughing is you really need to do the simulation for the previous operation. So what the re-roughing method does is it looks at the in-process or the current state of the stock model and then uses that as a starting point to create the cutter toolpaths. So
I'm just changing the thickness, line thickness of the toolpath so we can see it a little bit better. Okay, so there's our re-roughing. Let's go ahead and simulate that. Okay, So we got re-roughing.
Yeah,
Let's
so you
turn
can
that up.
yeah, so you can see you can only cut the areas that the previous operation left behind. So
And you
it's
can
very
do this.
important.
You can keep
Yeah,
doing
go ahead.
this with successively smaller tools if you wish. In other words, you can simulate the re-roughing and then do another re-roughing with a smaller tool, and you can keep doing that, to your liking till you get it down to where you like it. But we're going to do some pre-finishing also, so that helps to remove some material. Okay, so let's just remove the toolpath. Let's see what that looks like. So it got some more material off there. We'll run with that. Okay, so our next operation, I do have two layers over here that I want to draw your attention to, mask 1 and mask 2. Mask 1 fills in these two holes right here, and mask 2 actually adds an untrimmed version of this surface up here. So we're going to be machining this, and this edge right here is going to be a parting line. So we don't want the tool to roll over this edge, so we got this surface right here. And you can create, what I did to create that surface, I just took the surface I'm going to machine, and in Rhino, I just did surface, surface edge tools, untrim, or let's see. There's the surface. So we just go to surface, surface editing tools, do an untrim all, and it'll extend the edges out in a tangential direction. So in other words, it's the exact same surface, but it's extended out.
Well, no, it depends. I mean, my clarification there, it really depends on how the original surface was built. If it was built, as a trimmed surface, yes, it will do that. But if not, then you will have to, create your own surface in Rhino. Okay. So one more thing, Don, can you turn off the stock display? It's a little bit getting, yeah, go ahead.
Yes, there we go.
Yeah. All right, thank you.
Okay, so I got mask 1 on. I'm going to do a facing on the top of this. So I want to cover these holes up, okay? And let's go ahead and I'm going to make sure that all of my curves are turned on, okay? So next thing we're going to do, I'm just going to do a 2-axis facing, okay? And I'm going to, just one second. Okay, I actually have the part on my other computer right here. So I'm going to go select, I only want to face this area, so I'm going to go ahead and select this edge right here, and then the outside edge of the stock itself. And it will treat the inner boundary as a core region. In other words, it won't pass that inner boundary. On the outer boundary, it knows that it's the outer boundary, so the tool will go past it. Okay, so let's go and pick enter. And for the tool, we'll go ahead and use the 1/2" end mill. Roughing, all this is fine. We'll set that to 0. Tighten that up. This is a finishing pass, so everything else looks good. Now, location of cut geometry, if you may already know this if you watched other webinars of ours. I won't go into this in a lot of detail, but I will just say that the cut geometry is at the bottom of the cut. So it's right here on the surface of the block. And I'm going to set the cut depth to 0, meaning there's only going to be one pass on this surface. And let's go ahead and do some some arc fitting. 2. Let's generate that. Okay. So here we got a nice facing operation on the flat area of the block. Let's go ahead and simulate that. Turn that off. Okay. So now let's move on to some pre-finishing. You can use your finishing operations for pre-finishing operations just by applying a stock value. So what we're going to do is let's go ahead and get rid of that so I get more room. So I'm going to go ahead and do a 3-axis parallel finishing operation. This is just a standard parallel finishing. and it's in every configuration. So for this, we're going to go ahead and select, we're going to turn mask 2 on, okay? And we're going to go ahead and select this curve that I have right here. So it's an offset from the actual parting line. I have it offset. So I'm going to select this edge right here. And I'm going to, for the tool, I'm going to go ahead and use, just one second. We'll go ahead and use a 1/4 inch ball. Let's see where that is. 1/4 inch. 1/4 inch ball mill. And let's see what else we got. Feed and speeds, clearance is all the same. Cut parameters. We're going to go ahead and default tolerance. Okay, we'll just tighten this up just a little bit for a step over. Again, your step over will be tighter. Let's do 0.1. And no Z containment. If you look on the cut parameters, I do want to set a positive stock. Okay, so this is a pre-finishing, so I don't want to cut right on my part. And let's see what else we got here. Arc fitting. 2. And let's generate that.
Well, one of the things I wanted to point out is Don always sets the arc fitting tolerance to twice of that machining tolerance, if you've noticed. And that's one of the best practices. We let all our customers know. So that's a very good practice to have. So always make sure that the arc fitting tolerance is actually at least double that of the actual machining tolerance.
So I actually made the step over tighter than I intended. But if you look, here's the parting line. So we extended past that. As a rule of thumb on a parting line, if you're unfamiliar with molds, only cut the parting line once. So in other words, you only allow the tool to touch the parting line in any direction one time. So this, we're not actually on the parting line yet because we still got some stock on the part, but the toolpath extended past it. So let's go ahead and we're going to go ahead and clone that operation. And we're going to edit it. And we're going to change the direction to 90. This time I'm going to make the step over a little bit bigger. 0.05, say. 0.05. Okay, everything else should be the same. Let's generate that. So what I'm doing here is I'm running parallel finishing in both directions along the X and along the Y. To remove some excess material. So let's go into the, let's go ahead and turn the toolpath off and we'll run this. This is, again, a pre-finishing. It's leaving 25 thousandths of stock material on the part. And if you don't want to watch it, it's almost done though. Okay, so there it is in one direction. That is probably sufficient. I don't think we'll even need this one. So I'm going to cut this out. Because this, again, this is pre-finishing. It looks pretty good, so I'm going to continue on. So the next,
I think you used a very tight step over on that as well. So
yeah. Okay, so next thing we're going to do is a professional toolpath called curve machining. In curve machining, the toolpath will follow a curve, and you give it a bandwidth, and it will project that curve or toolpath down onto the surface. So let's go back over here to the part. Right now, we don't need this on yet. We'll go ahead and turn that masking surface off. So what we're going to do is we're going to go to 3-axis and we're going to do curve machining. And for the curve, we're going to go ahead and select, give me just one second. Okay. We're going to go ahead and select this curve right here. Okay. And this is offset from this wall, actually. We don't want to cut this wall or touch that wall. So we're going to stay off of the wall. by this amount. In fact, let's go ahead and remove that and select this other one just to make sure that we're plenty enough away from that wall. Okay, and then for the tool, we're going to use the 1/4 inch, looks like it. I know we're going to use the 1/8 inch ball mill. So let's get the 1/8 inch ball mill, and we're going to go with cut parameter here. We're going to do 0 stock. This is a finishing operation, and we're going to go along the curve. So it's going to go around the curve, and we're going to do a cutting bandwidth of, I think that should be okay. Let's try 0.2. And for a step over, let's go.
Values look bad there, Don. You got 0.02 on the bandwidth.
Okay, yep. Bad habit. 0.2. And for the step over, let's go 0.05, just so you can see it good. And for the entry and exit, we'll just use a lines entry and exit. Let's generate that. And you'll notice that the curve machining is a relatively quick calculation. Okay, so it looks like we're doing on both sides. That's not what I wanted. So let's go back into edit the operation. Cut parameters. Okay, left side. We're going to turn that off. And let's go ahead and change this to, give me just 1 second. Okay, let's change that to the right side. Right side. We're not going to do both sides, and we're going to have a bandwidth of 0.2. Okay, so what you see here is that it followed the curve. It doesn't matter if this curve is actually on the surface. It's probably close to being on the surface, so that's fine. And it will step over on the side that you pick by the step over amount. So I'm trying to get over here. I'm going to do it from this side as well. So let's go ahead and actually go over a little bit more. So let's go 0.3. Okay, so now I'm going to use the same operation. Again, I'm just going to clone it. I'm going to go into here, and I'm going to remove that edge, and I'm going to select this one here. There should be one there. Okay, so I'm going to select that curve, right click, and let's see if it's on the right side. Let's go ahead and generate that. Okay, yeah. Okay, so what I did here was I used 2 curves, 2 operations. One of the curve is on this inside edge, another curve is here on the outer edge. So the first one went from here outward, and the second one went from here inward with an overlap bandwidth, okay? We can go ahead and simulate that even though there's a large step over. Let's just go ahead and simulate that anyway. Okay, let's turn that off. So you see that it went from this edge outward. Now, ignore the cusp because I'm using a large step over. So let's go ahead and simulate this one. Oh, sorry, I didn't mean to generate it. Simulate that. Okay, so that is a finishing operation for this surface that goes all the way around. If you see that, if you look at that, that surface is curved. It's contoured all the way around. It's not flat in any location, but the curve projection toolpath is good for these types of surfaces. So for the next operation, we're going to go ahead and use, just 1 second. We're going to go ahead and use a between 2 curves machining. We're going to program this upper surface up here. Again, this is a contoured surface in 3 axes. So we're going to use a between 2 curves. In other words, we're going to machine between this tangent and this tangent. We're going to use 3-axis advance between 2 curves. We're going to remove that. We're going to select these edges, one here and one here. Looks like I didn't get the curve. Okay, so we got the two curves selected, and we're going to go ahead and use the same 1/8 ball mill, cut parameters. Everything else looks fine. Step over 0.05, say. Okay, entry exit, all that's fine. Let's generate that. So it's going to morph the toolpath between the two curves on the surface. So you turn that on. So you see, we've got a really nice toolpath. It follows the curves, and it follows on the part surface. This is the best operation for this type of surface. You can't get any better than that. With a tighter step over, this will be a perfect surface finish on that part. Okay, so let's go ahead and do another between two curves machining. And we're going to do from this edge all the way down and out to one of these curves. So we're going to go ahead and just clone this. We're going to go into the operation. I'm going to remove the edges, and I'm going to select with the top edge. We're going to use a different operation for this fillet, so I'm only going to go, well, actually, I can go all the way up. We use that curve, and then we'll come down to this edge, this curve here. So it's going to morph between those two curves following the part surface. So we're going to go ahead. Everything else should be the same. Let's just generate that. And again, the between two curves is a very quick calculation. So if you can utilize the operations that calculate quickly and still machine your part the way it needs to be machined, it's a double bonus. So you won't be sitting there waiting. So we had a nice tool path wrapped down around that fillet all the way down and out to this curve right here. So let's go ahead and see if we simulated that. We didn't simulate that one. Let's go ahead and simulate that. Okay. So it went out to this tangent. I want to turn that part on. It went out to the tangent of that fillet. And then this one will pick up from the same tangent and work its way on down. So what's neat about this operation, if you turn the toolpath on, is that it's not like a horizontal finishing where, you know, as you get closer to horizontal, the distance between the toolpaths become greater or lesser depending on the topology. This is actually mapping the width of the paths onto the surface, even if it's a vertical wall. It's so similar to a 3D offset pocketing, okay? But you're using two curves from one curve to the next. That's another very good operation in your professional toolkit, especially for molds. Okay, so we got that one done. Let's go ahead. Actually, our final operation that we're going to show, well, two operations left. We're going to go ahead and do a profiling operation around this edge, bottom edge. So let's go back over to here. We're going to go two axis profiling. Let's remove that. Sorry, let's remove all. We're going to profile around this curve edge right here. And we're going to go ahead and use our large toolpath, our large 3/4 inch end mill. And for the cut parameters, everything that looks good. We're going to let it determine the 3D model to decide which side it's on. You don't have to worry about that. And for cut parameters, did the cut parameters. For entry and exit, this is a finished parting face. So we don't want to run the tool on it, with a standard, radial entry. So we're going to do a ramp. We're going to ramp down into it. So let's do a nice ramp angle of, say, 3 degrees. And we'll leave a height of, say, 0.1. And we'll go ahead and do none for the retract. So it's just going to just pull straight up when it's done. So everything else looks good. Let's go ahead and generate that. Okay, so you'll see that we have a nice gradual ramp coming down, touching our parting plane and then cutting. Let's go ahead and simulate that. Let's slow that down so you can see that. So it's a nice gradual ramp coming around and cutting that sidewall. Okay, now that's pretty much got it machined, except for this inner pocket in the middle. And that's why I had this 2 operations down here that take a while to generate. So I just want to bring those up and show you what they are. So let's go ahead and drag this up there. We'll actually put it up there. It's a 3D offset pocketing. And let's go ahead and simulate that. And let's speed that up. So what that is doing, it's working its way around this fillet edge right here, wrapping down around and doing all of the inner portion of that pocket. Now,
and let me say a few words about the 3D offset pocketing, Don.
Yep.
So what this method does, it's a little bit different from the 2D offset or projection pocketing that we do. In the projection pocketing method, we take the 2D curves, offset it in 2D, and then we project the curves down onto the bottom. Mm-hmm. So what happens in that case, when you have vertical surfaces, when you project 2D curves, you might leave a lot of, this cusp height. The cusp height could be large in vertical areas. Mm-hmm. So if you wanted to fix that type of issue, you can use this 3D offset pocketing, which actually does the offset on the surfaces below. Mm-hmm. It's a very sophisticated algorithm behind it, mm-hmm. and it actually takes the curve and offsets the curve based on the surfaces below. And it's really not doing projection, mm-hmm. It's actually doing offset on the surfaces. That's why you see close to the vertical areas, you see the offsets, the vertical offsets seem very constant all around. As you can see, even in the flat areas, it's the same constant offset. So this will leave a very uniform cusp for you. Mm-hmm. So it's a pretty nice toolpath method to use.
Yep, and this toolpath, this is the only, for this particular part in this demonstration, this is the only finishing pass we need on this whole inside area, this whole pocketing area. And I like to mention too about the 3D offset pocketing. If you think of a fishing net, okay, and you're just throwing a net, that fishing net over the part, it's just going to adapt itself to the part surface, okay, with the same offset. Obviously, in the fishing net analogy, there's no net going this way, but it's just going in one direction. But that's how you can think of it. Very good operation for complex 3-axis contoured surfaces. And it, this happens to be a pocket, but it could be any. It could be, just a relatively contoured area. It could be a raised area. It could be a sunken area. That doesn't matter. It's going to wrap onto that surface regardless of the topology of that surface. Now, the other operation in here that I wanted to show you that does take a little bit of time is Bally remachining. And let's look at this. This is similar to pencil tracing.
Which we haven't talked about really. So you have another part you can show this in, right?
Yep, I do have another part. This is done. So let's go ahead and just load our other. I wanted to show this in 5-axis as well. So
you do that, Don. Do you want to pause for any questions on this part? If anybody has any questions on the programming of this type of part, please go ahead and put it up in the chat window. Before Don loads the other part, we'll be able to answer that.
Okay, just 1 second.
All right, I think we're good to go. No questions. So
Okay, let's go ahead and open this 5-axis version. Not sure what that error is. Okay. Now, as I mentioned in the beginning, sorry about that. As I mentioned in the beginning, we have this programmed. You can do this in 3-axis, or you can do it in 5-axis. In 5-axis, you're going.
So Don, can you turn off the stock display again so we can see the toolpaths better?
Yeah. So let's just go through and look at them. I'm not going to program because we don't have enough time to program them all, but let's just show you the path. So we did this, the horizontal roughing, that's the same operation. Basing is the same operation. On here, we did a 5-axis between 2 curves machining, okay? So very similar to the 3-axis between 2 curves, but the tool axis remains normal to the surface, and we can go ahead and just simulate that without stop.
Yeah, we'll probably do a webinar on the 5-axis using the same part to show the difference in machining using 3-axis and 5-axis. So we won't spend a lot of time on
the tool remains normal to that surface, and that is also we have a 5-axis swarf machining where the side of the tool remains tangent to that sidewall. And let's go ahead and run that. You'll see the tool remains normal to this wall here, tangent on it, and located at this edge. And then for another between 2 curves machining, right here on this surface, let's go ahead and zoom out a little bit and show you that, where the tool axis changes as it runs along that surface. Okay, so then we have a curve machining similar to the advanced 3-axis. The profiling is the same. And then we have another, we did this in a swarf operation. You can do that as well, and it'll run around on that raised core face right there. And between 2 curves for filleting this edge. And then also we have the same 3D offset pocketing. What I wanted to do was I wanted to show you, let's go ahead and play this. Okay, doesn't look like we have a machine defined. I was going to show you a machine simulation, but I don't have one defined here. If you want to, we can go ahead and do that. Let's pause that. We'll go ahead and pick one. Let's just pick one, see what it looks like. Okay, let's go ahead and pick another one here. Okay. Okay, let's just pick one. And let's simulate that again. Turn our machine on. Turn our stock on. Doesn't look like we're getting the stock displayed for some reason.
I have a holder turned on too, so yeah, don't worry about that machine.
Yeah, I'll do that in the. What I would do is I'll go ahead and record it, the 5-axis machine tool simulation, and we'll put that in the recording as well as an add-on to the video. Okay, so I wanted to show you another let's stop. Another part which illustrates some things that I wanted to show you. So we're going to run the, let's run this mouse. Let's turn the stock off. Now you might think, well, that's a pretty simple part, you know, nothing to worry about there, but it's not simple. The reason it's not simple is you've got this edge that contours around this ruled surface. So we need to make sure that we don't overcut it, but we need a nice clean edge along there. You cannot, well, you could do it in standard, but you're not going to get a good surface finish because you don't have the tools and the control as you do in the professional configuration. So I just wanted to show you what we did. And also there's a draft angle on this part, okay? It's not actually on the part. I did it by adding a tapered tool. So let's go ahead and just do this simulation. I'll show you what I'm talking about. Let's go ahead and simulate that. That's the roughing. We did a re-roughing. And then we did a parallel finishing with stock, pre-finishing, with we got stock on there. So let's go ahead and simulate that. Let's look at what that toolpath looks like. So we just ran a parallel finishing over the top of the part like we did on the previous part with stock. Okay, so let's go ahead and simulate that. So we're just pre-finishing, get a lot of material off. Again, we did one going this opposite direction.
You're using a tapered tool on this.
Yep, yep. I believe it's a 5-degree taper. Let's see what it is. It's a 5-degree taper. And that will get, again, if you have draft on your walls, if you notice this part had no fillet and it had no draft, if you need to, you have a fillet at the bottom of your part, use and it also has a draft, use a tapered mill that has the same draft angle and the same ball radius on the mill, and it'll cut those for you. So we got, on this next one, we have our finishing operations for the actual parting plane right here. So we use 2 curves. I don't look like I have that curve displayed, but it just cut between these 2 curves, an inner curve and an outer curve. And let's go ahead and simulate that real quick. And again, I used a smaller taper mill with a smaller ball on it. I used a 5-degree taper mill, same draft, but with a 1/16 ball. Okay. So let's go ahead and do this one in the opposite direction. Turn the toolpath off. Okay.
So it looks like it's the same direction though. Y direction, X, maybe.
It should be the opposite. Let's turn that on. That's going that way. This one's going the opposite.
Yeah, okay.
Okay, so the parting surface here, out here, is all done. Okay, so now we're going to do a 3D offset pocketing like we did on the other part. And we picked an edge that's offset from the corner. So the tool is going to go all the way down and out and all the way around that top surface. And I'll show you what that looks like. So we're just going to work its way out. I have a large step over too. So you see the cusping. This path works good. Use the largest ball that you can, okay? Only because the way the toolpath wraps on there, you may see some excess areas right here. So with a larger ball, you won't see those. With a real small ball, you want a smaller step over, so you make sure you get rid of these or get a smooth surface right across the center there. Okay, so let's pause that. Okay, let's stop that. And then also a valley remachining. Again, we're not selecting any geometry. Let's go into this operation. You'll see. And this actually, between this and pencil tracing, they're very similar. But I think the valley remachining actually does a better job. So let's look at how this is done here.
Well,
So,
the pencil tracing can be used as a pre-finishing or a roughing operation. And then the valley remachining is really, as we say, it's a remachining or a finishing operation.
yeah,
So
good point. Okay, so we're not selecting anything. We're going to let it calculate the areas. Now, what it's doing is it's calculating the bitangent location of the tool between the surfaces. So we have a distinct, almost right angle right here. So it's going to calculate where the ball touches this surface, where the ball touches this surface, and then it's going to add an offset to whatever we want. So we got a tool here. We got a 1/16 ball mill and cut control. We got, really, I don't know why I had such a tight tolerance there. That must have been a typo. And on this one, you can use a tighter tolerance to get a smoother path. So I'm going to just loosen that up. Stock is 0, so it's a finishing path. Here we're telling it, what was the diameter of your tool that you used prior to that? Even if you didn't use the exact diameter tool, this value is determining the width of the cut, okay? So you want it to be at least the diameter of the previous tool, okay?
and one more point there, Don, I want to explain that reference tool diameter is what we use internally to compute the bitangency cuts.
Mm-hmm.
That tool, we actually create a temporary tool using that tool diameter. We use a ball mill, and then we figure out the bitangencies of where that tool is touching on both sides of the surfaces, and then create a cutter path. And that cutter path, or path, if you will, and that path is then used to create the valley remachining toolpath using the actual tool. In this case, it was a 1/16 that Don selected to create the actual machining toolpath. Hope that makes sense.
And again, you can experiment with these to see all the different parameters. We have some additional cutting parameters. You can break the toolpaths up depending on the angles of the geometry or the bitangent. And also for determining, whether the toolpath is going to be along the edge or across it. We have it running along the edge, and we have a step over of 25% of the tool, okay? And let's go ahead and simulate that. Slow that down just a little bit. So it's beginning tangent to the sidewall surfaces, and it's working its way down, remaining tangent till it gets to the bottom surface here. And then the last pass on the bottom will be a bitangent pass, and then it's going to work its way out tangent to the bottom surface. So this is the ultimate finishing toolpath. If you have a contoured surface, 2 contoured surfaces, this is the type of control that you need to do molds. You can't get this kind of control in the standard configuration. And then here is we mentioned the pencil trace just goes around in one pass. Okay, I do have one other part. I'm not sure how the timing is going because we started a little late, but I'm going to go ahead and take a moment to show you one other part. And let's open that. Turn this.
You have another 15 to 20 minutes on this, Don, so you have plenty of time. So
okay. So on this particular part here, we have a lot going on, obviously. So we have masking surfaces to mask these holes, in the contour. And if you're familiar with the way mold machining works, these areas up here will not be machined on a 3 or 5 axis. They'll actually be burnt in with a electrode, an EDM electronic discharge machining electrode will actually burn these pockets right in there. So it's very precise. And we also have a pocket down here that should be burned in. But what I wanted to show you was the pencil trace as it moved along that bitangent area. Okay, and on this one, let's see where they don't look like I show my actual control geometry. Let's go ahead and run that. Turn that off. Slow that down. So it's remaining tangent to this wall and this bottom surface. I don't have a bandwidth or cutting width set, so it's only doing one pass. And on the valley remachining, it's
the pencil trace. You cannot do a bandwidth. It's just a single pass, so that's all it does.
Okay.
Only on the valley remachining, it uses the reference tool to figure out how wide it needs to go.
So if we go back into the valley remachining, you see that we have a 5mm tool that we used previously, and then that will determine the bandwidth of the tool path. And let's see what tool we used there. We used a 2mm ball mill. Let's go ahead and run that to speed it up just a little bit. So it's just running around that like a racetrack. Very precise. That's what you want to use if you have any bitangent area. It doesn't have to be a mold, it can be anything. Okay, so that's basically all that I had to demonstrate. If you think we've got more time, we can go back into our other part and do some more on it if you want to. What do you think, Joe?
I think you can bring up the mouse part and then actually show the pencil trace and valley remachining, starting with the pencil trace. I think it'll be more instructive. And you can actually generate the toolpaths.
Okay.
We got about 10 minutes left, so.
Okay. So let's go ahead. We got all that. We did all that. Offset pocketing. And let's, sorry about the pop-up. For the valley remachining, again, go into
Let's do the pencil trace first, Don. I think that's, we are normally, typically on a mold, we start with the pencil trace. So we do the roughing followed by the valley remachining. So.
Okay, let's make this a little bit easier to see. Okay, so make it a little bit bolder. And let's go and look at the pencil trace parameters. Okay. I had these boundaries selected. You don't really need to select those. I'm not sure why I had them selected. So for a tool, I'm using a 1/16 5-degree taper mill, as I mentioned previously. For the cut parameters, 1,000ths tolerance. Everything here is fine, the default parameters. Advanced parameters. Let's go look at the cut parameters. Okay.
So yeah, you're right. You could do multiple cuts. Yes. Sorry about that.
You could check that and then do, if you want to determine a bandwidth, it'll do a bandwidth of cuts. So let's just leave that off for now. So cut parameters, advanced. Everything looks good. Let's generate that. Now you'll see that it does take a moment longer than a normal, like between two curves, or parallel finishing is probably the fastest operation that we have.
Doing a lot of computations there because it's computing the bitangencies. So.
And also, while this is actually, it calculated it, so it got one bitangent path around it. And let's go ahead and simulate that again. We can just simulate all of them. And if you want to go down, we can just go down to here, right click, and say simulate until. So we're just going to go through all of the simulations. Hopefully I didn't tax it too much. Okay, there we go. So we simulated it all. Now let's look at the pencil trace. Slow this down. And what I want to do is I want to do a 3-view port, and I'm going to play that so you can see down here. Let's pause that. Looks like it's playing. Let's pause it.
What? Oh, what? Okay.
I wanted them to see this right here. Okay, so let's play that. Speed that up just a little bit. So it's working its way down. And you'll see that it's automatically putting the 5-degree taper. And the 1/16 ball is tangent to these two surfaces here and here. Looks like it went all the way through. Let's run that again. And again, you can keep, depending on how sharp a radius is required or what you can get away with here, you can keep using a smaller ball on the taper mill just to get that as tight as you need to get it. Okay? And then
one other note on compute speed, Don, was taper tools notoriously take a lot more calculations, so
yep.
taper tools will run slower than the standard straight ball mills.
What we're demonstrating here is the power of the professional configuration, okay, with combination with both ball mills and taper mills to have as much control as you need for that tool on your geometry. If you have complex geometry like this, you really should be running with the professional configuration so that you have these toolpath types that you can use, and you can use them with any tool type that you need. Okay, so let's go ahead and run that.
Let's talk about that valley remachining also, or maybe even recompute it with a ball mill, a straight ball.
Okay, we can do that. Okay, we'll just leave it in a 4-view port. And let's go ahead and look at the valley machine again. So we didn't select any geometry. It will automatically calculate and analyze all of your geometry to determine your bitangent locations. And on this part, it's only going to find a bitangent in this area. So let's go to the tool. We got a 1/16 straight ball mill. And again, I didn't use a taper, so it's going to remove that 5-degree taper if I run it with the ball mill. So let's go ahead and do that and see what it looks like. Okay, cut control. Not sure why that was so tight. Let's go ahead and make this 1,000, 1,000. 0.2, I guess that'd be all right, 0.2. All of those, we're doing along the curve or along the bitangent. You could do across, it'll just work its way across all the way around it. That wouldn't be good for this particular part though. So we're going to do along, and let's just generate that. That was fast, Joe. That was faster than I thought it would be. Okay, so it calculated that almost instantly, Joe. And if you do that with a taper mill,
I think the ball mills, straight ball mills are, as I mentioned, performance is much faster than the taper mills. So
if you want to, we can go ahead and change the tool if you want to see the difference. Taper mill 1/16 5-degree. That was task 2. It looks like it didn't go all the way around though, did it? Not sure why. Let's go in here and see if we need to tighten that. Maybe that's why I had it tighter. Okay. Well, Joe, it looks like we still got a full crowd with us. So again, we apologize for the technical difficulties. Okay, so it's still not going all the way around. I'm not really sure why. On the other part that I have on my other screen, it's fine. So when we send you the parts, if you ask for these files, it will be generated correctly. I'm not quite sure why it's not doing it. Okay. Well, we got any questions, Joe? That's about all I have to present. Let's go ahead and see.
Actually, there's a couple of questions I would like to take this opportunity to answer. The first one was from a customer was asking where they can see the previous webinars, and the response to that is if you're an AMS customer, you actually only, this is available only to AMS customers. So you will be, if you have previously registered for our webinars, you would have received a recording, an email recording, a link to the YouTube recording of our webinars. But if this is one of the first times you're joining us, you could go to your portal, your customer portal, log in there, and you'll have a link for a CAM Jam video link, and you can pull that CAM Jam video tutorials, which is about, I think, over 80 videos down.
Oh, it's many more than that. It's over 200.
Yes, over 200. Wow. Videos that showcase different features of our product. So if you haven't seen that, we strongly urge you to take a look at that. Mm-hmm. It'll answer a lot of your questions. And then as far as there was another question about horizontal roughing, adding a lot of retract moves. So yeah, unfortunately, horizontal roughing, what it does, it splits up because of the nature of the machining, it splits up the area into multiple areas to machine. And so it necessarily has to retract from one area to the other. What Don's showing here is of our facing toolpath. And again, as it splits up the area, as it cuts from one side of the material, it always tries to engage in the material from the outside. And which is always a good thing because you're not engaging into material. So that also necessitates us adding a lot of retracts.
Would the retracts be less if we used a different cutting pattern?
If it is inside cutting, if it's in a certain area, in a single area that was split off, yes, it would. But then if the machining itself splits up the areas to machine into multiple areas, then it won't. Oh. Yeah. For instance, if you use pocketing, it'll definitely reduce that. So.
Okay. So let's go into pattern.
Do offset. Do offset. Don't do high speed. Oh, yeah. Actually, core facing. Yeah. Do even. Linear. I don't know. That's fine. Yeah, that's fine. Hit it. Generate. Let's see what happens.
That was, I believe, what I had before.
Okay. So again, we're trying to engage from outside, and that necessarily, introduces a lot of cut areas. So if it's a pocket, you should have a lot less, retracts. So
again, what you're saying, Joe, is actually something that I didn't know. It subdivides the geometry internally. Is that what you're saying?
Yeah, it splits up obviously because think of it as you're machining, you're slicing the model with the plane. And that will create islands, separate individual areas to machine.
Okay, I see.
So for instance, this area, right? So it split it up into two areas. So it needs to necessarily retract and go to the other side.
Mm-hmm.
Machine, yeah.
So. Yeah, and you can't get around that because it's all dependent on the shape of the geometry.
Yeah, this is especially true in the horizontal roughing and re-roughing methods. So. Mm-hmm. And then, as Don mentioned, other toolpath methods might help reduce the retracts and engages in a split off in a single area that you're machining. For instance, there you really don't have a retract in that area, but in some cut methods might introduce a toolpath because of pinch offs.
Mm-hmm.
If that happens, using a different cut method might help reduce it. So
Mm-hmm. Mm-hmm.
hope that answers the question. So
okay, again, I want to mention that if you want these part files, the start parts and the final machine parts, send us an email to support@mecsoft.com, and we'll send you a download link for these part files, and you can work through them on your own. Okay. Okay.
All right, everybody. Apologize again for the delay, and we will clean it up, and then we will send you the YouTube link. Thank you very much.
Yep. Thank you, everyone. Take care.